I'd like to welcome you all to our session today on digital twin. In particular, we're going to be talking about Emulate 3D and the interaction with FactoryTalk Echo. With us, we have Michael Sarvo from Rockwell and Kene Azinge. They are our subject matter experts, and I'm not going to spend any more time talking. I'm going to turn this over to Michael, who I believe is going to kick things off. Mike, thanks for joining us. Looking forward to today's presentation.
Hey, thank you very much. Appreciate being here and having everybody's attention to share my favorite thing in all the world, and that is Emulate 3D technology. So I'm Mike Sarvo. I come from Emulate 3D. From way back, I was a customer of Emulate 3D starting in 2007. So I've been using the software for over 17 years and joined the company in 2013. We were then acquired by Rockwell in 2019. I now do business development in North America, but I've done everything you can do with Emulate 3D, support management, applications engineering, sales even for a little bit. And what I love to do is just share it with the world. Kenny? I can't hear you. I saw that you unmuted, but it's not working.
Can you hear me now?
Yes.
Of course, this is recorded where my audio messes up. Finally converted over to the new Teams. But yep, my name's Kene Azinge. I am a local software and control technology consultant based out of Philadelphia. So I help deal with all the advanced software and our controller hardware and HMI systems. So I'll be helping to talk about Echo, show some of the advantages, and just show you a quick tour of the software.
Thank you, Kenny. Hey, I'm going to share my screen now, and hopefully that'll be visible to some people. Hopefully to everybody. That'd be great. Can you see that?
Yes, we can.
Awesome. All right. Thank you so much. Right. So what brings us here today? This is kind of the conversations that we have with anybody when we first start talking about what we can do with this technology and how it can help all of the people in the world. Right. So there are challenges that we're facing in the industry, and not just OEMs, not just system integrators, manufacturers, everybody, end users. There are a common set of challenges, and some of them are things that we think we can really attack and correct and mitigate with digital engineering technologies, like we're going to talk about today, and some very specific bits here around labor and access to things, access to equipment and parts and all the things that we experience with supply chain, and getting machinery in front of us so that we can test and debug and commission our controls. And when you can't have access to equipment and you can't get the right people access to the equipment, you have a problem. And we think that we can sort that out using these tools. Here we've got one more person joining. There we go. Thank you. So that leads us to digital twins, and what is that, right? So for us, digital twin is a computer model of a thing or many things, a system of things, and we build these different digital twins based on very specific purposes. So you probably won't ever set out to build a digital twin that is the is-all be-all of a thing, because that's a lot more information to pack into a model than what you'll ever get any return out of, right? So we build models for specific purposes, and some of those purposes are to understand the capabilities of a system that we're proposing or building, so that we can share that information with our clients and explain that our offering is going to meet their needs, whether it's throughput or the OEE on pieces of equipment, things like that. So we build simulation models in Emulate 3D. These are a kind of digital twin, and we use those models to prove out capabilities of our designs. Another thing that we do is actually use the models as just dumb digital machinery that does no better than exactly what we're telling it to do with our controls. So when we do things like connect up Logic's Echo, to the digital equipment in Emulate 3D. Now we've got digital PLC, digital equipment. We bring together these things, and they become a digital twin of the machinery system with its controls, and we can test and debug all of our control logic before we built any real equipment. So that's the kinds of things that we see to do with these digital twin technologies. In the market, over the past several years now, we've been seeing some issues revolving around supply chain and access to things. And later on, I'll show you even an example of an internal example. There's a guy that we work with named Motion Mike, who's done a machine that he had built for demonstration purposes, but he didn't have access to some things that he needed. Some of the parts were not going to be delivered on time or in a early enough fashion that he could do his virtual or his controls commissioning while being able to test the controls, because he wouldn't have had the real equipment. So he used Emulate 3D to build a digital twin of the machinery, and then can connect up his controls to that digital equipment. And now the lack of real equipment is just not a problem. We designed that out of the commissioning project by having digital twins rather than reliance on physical equipment. Another area that is important to think about is getting the right talent where it needs to be. When you have to associate physical location with talent, the pool gets much smaller. But when we can remove that restriction, the pool is much larger, right? So we can find talented engineers who can do this controls test and debug and modeling against digital twins, because they can do this remotely. The digital twin can be anywhere. I can email one to Kene right now and he'd have it, right? And he could connect up his controls to it and start testing that stuff out. No problem. You can't do that with real equipment. So you gain lots of advantages by being able to have your own digital twin of the machine, and all of the engineers working on the system can have their own copies and can be working on their individual disciplines or parts of the system completely in parallel. They don't have to be fighting for access to the stuff in order to move on. There's my clicker. So what we say we do with Emulate 3D is virtual commissioning in the end. There's a few things that kind of lead up to that point. But when we do virtual commissioning, we are bringing together the truths in automation. And to do that, we don't try to be all of the different tools that everybody already uses. For example, the CAD. We're not CAD. Emulate 3D is not CAD. A lot of times people will take their first look at it and they say, oh gosh, that's a 3D CAD platform, but that's not the case. CAD is not a competitor. CAD is our friend. We import all kinds of CAD and turn it into digital machinery. And so you use your CAD, whatever CAD platform you happen to be using, and we can turn that 3D geometry into controllable machines. And we even have some special tools that allow you to do a lot of that work in the CAD platform itself. So we'll talk about later what we call CITM, or CAD is the model. These are plugins that we put into SolidWorks, Inventor, and PTC Creo so that you can bind Emulate 3D functionality to the CAD while it's still in that native format. And so you work in your CAD, and we bring that together into Emulate 3D along with the logical truth. So this is your control software, your control logic in the piece that you run in the PLCs. And again, we don't try to import PLC programs, and we don't try to recreate it in some kind of pseudo language, right? I mean, if we're doing simulation, we have simulation logic. But when it comes to commissioning, we just connect. Again, just like we connect to CAD to get the geometry, we connect to the controllers to have the controllers talk to the machines. And so you write your PLC code the way that you always would. You deploy it in the way that you always would. And now you've got a way to digitally test all of these things together. So that's great. You could have the digital machinery and the controllers hooked up in your HMIs, and you can start jogging axes and flipping bits and things like that, and seeing the different pieces of the machine move. And that's really helpful But what about really stress testing that equipment or putting that equipment into the context of the real production environment, or even better, something worse than the intended production environment, so that you can really create robust controls that will handle all the different situations that you could ever expect? That in and of itself can be really challenging to do in real life, even if you have the equipment set up on your shop floor, because you need parts to process. And in my background, when I was a customer, I was a system integrator OEM for automotive powertrain material handling automation, and I would get a pallet of like 6 engine blocks, and I'd have to load them up one at a time with a cherry picker, put an engine on a cart, wheel it over to the front of a line, manually cycle it on, and then repeat that process 6 times before I can go around and start up the machine to see how my first run is going to go. And that's a lot of time and energy put into just doing a single test. But then on top of that, what am I going to do with 6 parts? That's not a stress test. That's not even enough to try to begin to create a logjam kind of situation or anything like that. So when I'm in this digital environment, I can create as many parts as I want. I can introduce flawed characteristics in the parts and see how my systems handle all the different kinds of situations that we might ever expect to encounter, and have all of that done before we've ever built any equipment. And then, of course, there's one more thing that we sometimes need to consider, or probably should always consider, and that's, what do we do to everything, right? What about people? So we can simulate people in this environment too, but we can go further than that, and we can actually even be the people. So what I mean by that is, Emulate 3D, when it's running, right, it is a volumetric physics environment that you can interact with through the screen. You can use your mouse and reach out and click on an object and stop it where it is and drag it and move it, or click buttons in the model and see how everything happens or reacts to the things that you're doing to that machine, just like you're standing there. Then you can even go a step further than that if you really want to gamify the environment. Every Emulate 3D model is also automatically a virtual reality model. So you can put on a headset and you can go into that model, or you can have multiple people join as well. So if you want to do a virtual walkthrough or walk around of your equipment or facilities, you can do that while it's a live running intelligent model. So we save, right? This is kind of the whole aim for people to use our software, is to save time and money. And we do that across the whole project kind of life cycle. And we've designed our product to have some different characteristics that add value to these different phases of a project. So we'll talk about in the next slide what Demo 3D means, what Sim 3D means, and what Emulate 3D controls testing means. And those are different, they're different activations or licenses for Emulate 3D software, but it is all one piece of software. And the Demo 3D, the demonstration, we use in the upfront phase of the project, and we shorten up the decision-making cycle to move forward with the project by making it easy for people to put together media that you can share with all of your internal and external stakeholders and bring tremendous clarity to the situation very early on, right? And when we're talking about complex things, it's clarity that brings everybody together and allows us to make decisions. So when you look at an Emulate 3D model and you can see all of the moving parts and see where the materials are flowing, it's believable. You can see it and you can understand it, and all the questions are answered much more clearly. So we can begin the design cycle, the hard design cycle, sooner in the project life cycle. And as pieces of that design begin to harden, as we start to understand what the equipment is, we can build out the digital twins of those pieces of equipment and already begin your commissioning of your control logic against those digital twins much earlier in the project than in a traditional plan, where you can't really debug and test your code until after you've built equipment, because you have no signal feedback. You've got nothing for that controller to send commands to and receive feedback from. But when you have digital twins of the equipment, of course you do. And so you can have all of your control logic tested and debugged and even debugged better before you've built the equipment, before that equipment has shown up on site, before the first operators ever touch it. Now, since we have that digital twin, and we have all the control logic, and we've built our HMI screens and everything, what else can we do with it besides the fact that we've commissioned it early? Well, we can also do things like train our operators. So it is a full-blown system, all of the logic, all the operation, everything's there. And you can have multiple copies of it, of course. And so you can start to introduce your operators to the system, walk them through the operations, train them on how to use it, how to interface with it, how to deal with exceptional situations before that machinery ever hits the floor. So the first time that an operator sees that equipment doesn't have to be the day that we turn on the power on site and try to begin production. So that then gets our end users time to market greatly reduced, right? And we'll see an example of that in the next couple of slides when we look at a couple of customer stories, okay? So customer story number one, customer named Indicon, and I'm in the Detroit area. These people are in the Detroit area, and they do a lot of automotive work. And they came to one of our user group meetings. So we have a big user group meeting every year, usually in October, where a bunch of our customers come and they tell us about all the wonderful things they've been doing with our technology. And in return, we tell them about all the new features that we're packing into the next build. And everybody gets excited, and we all love each other, and we have a great time. So Indicon came in and they said, hey, over the past year, we've done these 9 projects. 2 of them we didn't do virtual commissioning on, and 7 of them we did. Well, those 2 that we didn't were over time and over budget, and the 7 that we did were all under on budget and all under the target timing for it. So proof is in the pudding, right? This is not us saying it. This is customers telling us, hey, you guys were right. So that's fantastic. And of course, the challenges, just like we talked about early on, some of the challenges that they're facing is that access to equipment and, and wanting to not have to be on site necessarily to do all of this test and debug. There's no traveling, so the cost of doing it all is reduced. And they're able to just get this work done before any machinery is built. And in this particular case, this isn't a video here. I do have a video of this. I don't know if I have it in the slide deck, but these guys even found a problem that they weren't even supposed to be looking for. So they were doing controls, test, and debug on this system. And I don't know if you can tell what this is, but this is a skid, an automotive skid, and this is a vehicle chassis. And this is being lowered onto this skid. And as they're testing the controls to make sure that all the pieces did the right motions, they noticed that there was a collision. There was they would have broke stuff had this been in real life. They would have broken this equipment. So they were able to report this design flaw back to the mechanical engineering departments, respectively, and get this stuff fixed before they built any equipment. So they made these design changes before they had to scrap anything that they actually made. And of course, that's just one more dimension on how we can save time and money and energy using digital engineering technologies. Another example, this distributor of spirits, they had a plant like this, some old traditional kind of storage and conveyance systems for their distribution, and they needed to increase their capacity. So business has been great. They need to do more, and they didn't want to have to grow the physical footprint of the plant or add another plant. And so they looked at some newer technologies, both in equipment and then, of course, the technologies to actually operate all that equipment with all of that new capacity that they're bringing in. Well, their workforce, right, doesn't know this new technology, both the equipment and the operating system for the equipment and for now the overall architecture of their distribution center. And so they used Emulate 3D technology to build digital twins of this environment, and were able to mitigate the risk and have confidence to move forward with the project, get it done earlier than expected, earlier than what you can do doing traditional means of deployment, and train their operators so that their operators were ready to start this system up and get value out of it on day one. And then one more, there's my clicker, one more example. So this is, these are these carburization machines. They basically infuse carbon into steel, and they're a very complex machine, and the systems are massive that they build. And the complexities there are many complexities. One, testing a large system is inherently difficult. So in real life, to really commission it, getting everything all powered up and synchronized and working together, to go around and test the overall logic that controls, the individual machines and the overall system architecture is just a difficult thing. But when you can shrink all of that down into a manageable model, that becomes easier to deal with than it is to deal with in real life. For restarting and resetting all of the conditions to do each test as they continue to build out and debug all of their control logic. And another thing that Emulate 3D provides here is connectivity to other external things, right? So controllers, robot simulation software. So for example, FANUC RoboGuide, we connect to FANUC RoboGuide so RoboGuide can control the robot and emulate 3D. Well, these machines have very complex signals that they rely on for testing and debugging and tuning on the systems. And so they were able to use our MATLAB plugin and run their MATLAB models that represent the complex physics of these devices so that they could truly test out not just the sequential logic of the machines, but how they deal with PID loops and stuff like that, right? And so remember the timeline that I showed you a few slides back where we said, hey, in a traditional commissioning, you have this kind of lock-in step phases where you design, you build, you commission. This looks a lot like what I was showing you, and we were really over the moon when these guys came in and presented this to us and showed us the savings. What we weren't expecting, though, was just how massive the quantity was that these guys are reporting that they saved on this particular project. So they shaved 5 months off of what they were expecting when it came to commissioning this one particular system, and gave their end user such confidence in them that they immediately were awarded 2 more contracts. So not only did they save themselves money, they saved their client money, they got them their time to market improved. They now won additional business from doing this kind of activity. So you just continue to win over and over using this technology. So I've told you about why and who and what for and what you get from it. But now I want to talk about the technology itself so you can understand, really what it is and how it works. So Emulate 3D is really at its core, it's designed for any kind of discrete material handling operations, all of the automation and things that move parts, take parts apart, or put parts together. So if you think about what that is, right, it's any kind of automation that moves things throughout a system. So conveyance, robots, independent cart, AGVs, fork trucks, all of those kinds of things. When we talk about putting things together, this could be assembly work, it could be packaging, you're putting things inside of a box, or palletizing and taking things apart, just the inverse of that. You decant, you depalletize, you take disassemble, whatever those operations are. So our software has been built from the ground up to just inherently make that kind of work easy to model. Now, in addition to this, we've recently, and I say recently, over the past several years now, three years, have developed a fluid handling system so we can do process work as well, and for the purpose of controls testing. And so that process catalog that we have is designed to connect up to Plant PAX as well, to utilize all of the kinds of structures, control structures that we have there. So remember Demo 3D, Sim 3D, and Emulate 3D and how they relate to the project timeline. Demo 3D is, when we think about it, is kind of the base of the software platform. It's the core. That's all of the physics. It's the catalogs of over 800 things that you can drag and drop and build the models with. It's importing the CAD. It's turning that CAD into machinery. On top of Demo 3D, the Sim 3D license adds to your experience design of experiments, and analysis tools. And these are tools that let you build programmatic execution of experiments where you change variables about the model per experiment and use the analysis tool to collect the data about the model so you can do reporting on it. And then the Emulate 3D controls testing activation adds to your experience the connectivity to external controls. So whether that's PLCs, PLC simulators, or high-level controls like WCMS or WMS or MES, right? Those kinds of systems. So the technology that allows you to connect out to those kinds of systems is in that Emulate 3D controls testing. So here's a demo video, sample video, of what it's like to build a model inside of Emulate 3D using just catalogs. So you'll see in our catalogs, we've got all kinds of robots and a robot controller that will take anything that we say is a robot and turn it into a simulation-ready component or emulation-ready component that we can just control. Drag and drop conveyors, which are all parametric. You can stretch them out. You can change all the dimensions about them. There we go, another component that is a pallet destacker. It's going to feed pallets into the system. Some racking, storage racking, ASRS type systems with cranes built right into them. And now we're going to set up an AGV track-based loop, put in a few control points to help us direct traffic. And there we go, make a copy of our robotic palletization system. We're going to in-feed some product, put in some data collection, and we're up and running. So that demo 3D is designed to let you just do drag and drop model building so that we can create these examples and show our ideas to our internal and external stakeholders, again, so that we can very clearly express an idea and do it fast, right? So next example, this is using, oops, that's not the next example. There we go. Using the Sim 3D features. We build the models in the same way, but now we can, through a table, execute multiple experiments in batch. And for each experiment, we collect any data that we have data collectors for in the model. In this case, we're looking at the throughput of the model. And in each experiment, we're changing the number of fork trucks that we're using. And every time we do that, we clear out the model automatically, get it back to an initial state, and run it with the new input conditions, so the new number of fork trucks in this case. And each time an experiment finishes, we log the data, and we've got a chart here that's looking at the throughput in each experiment. And so this tells us a story. As we've increased the number of fork trucks per each experiment, we've had significant gains in production, all the way up until we get to 4. And after 4, we pretty well flatline. So there's no more gain with 5. There's no more gain with 6, just for good measure. And so what does that tell us? Well, if that's our production that we want, or if that's at least, if that's more than the amount of production we needed, then we've found the optimal number of fork trucks. Any less, and we were leaving a lot of production behind. Any more, and we've got operators just kind of sitting there. So 4 is the right number. Or if we're actually looking to continue to increase our throughput, this tells us that the fork trucks were the bottleneck in the system until we got to 4, and now the bottleneck has shifted somewhere else. And of course, we can put other data collection in to see where that other place is and change different variables about the model, just like we've done with the fork trucks, to find the next point in the bottleneck and continue to attack and resolve those bottlenecks until we've got the production that we're looking for. Now, this next video, this is Emulate 3D controls testing, but we're going to start out using some of the CITM, or CAD is the model, features that I talked about a little bit earlier on. And in this case, we're actually working in SolidWorks. So this is the SolidWorks platform. This is Emulate 3D toolbar in SolidWorks. And it allows you to touch all the different pieces of equipment in that CAD model and associate machinery characteristics with them. So here we're adding a physics body to that pusher and a joint, and the joint describes the degree of freedom that it's going to have, so how it's going to be able to move. And then on top of the joint, we'll stack a motor. And the motor says, well, how fast can this joint move? What's its acceleration and deceleration curve? And then on top of that motor, we put a control interface. Are we going to treat it like a spring return valve, or am I going to drive its position like a servo axis? Now we've just pushed that model directly into Emulate 3D. And what we're doing here is connecting up the PLC to the equipment, and each one of these rows in the table is the virtual wiring, sort of, right? It's binding a tag, a PLC tag, to a property on one of the components in the model. So the photo eyes have a set of contacts on them. It's got a normally open and a normally closed contact. And we just bind that to a respective PLC tag through this table mapping. The same thing for the pusher. The pusher is going to be an output from the PLC. We activate it, we push the loads across. And you'll see when the loads get to the end here and we do another push, you'll get your first glimpse here of that volumetric physics engine in play, right? And that is the parts will fall on the floor and we're making a mess already. And that's actually really good, because it means that this machinery isn't going to fool us. It's not doing anything smarter than exactly what we're telling it to do. So if we're controlling it really well, it's going to have a really good outcome. If we're not controlling it really well, it's probably going to make a mess, and it becomes very clear what we need to do next. So Motion Mike, this is the Motion Mike story. So he needed to make a machine, and he needed to convince some stakeholders to spend some money to build it. So he used Emulate 3D to design this machine from the ground up, and he also didn't receive some of the components in time to do the commissioning to get it done for the project that he was aiming to get it done for. So he was able to actually use that digital twin model in Emulate 3D, connect it up to Logix Echo, and test and debug all of his control logic, so that when he did finally receive the equipment, it was ready to start up. He was able to just deploy his code, and the machinery all functioned exactly perfect. He said, except the robot was 1 millimeter off on one of the picks or something like that. So he said within a millimeter of just completely ready to go right out of the box. Fault framework. Fault framework is a new development. So we're constantly pushing new stuff into the software. And Fault Framework is set to revolutionize the way that we do our controls testing experiments with Emulate 3D. So we've always been doing, you connect up your controls and you test and debug your logic, but the way that you would run tests against the machine was very manual. You would go into Emulate 3D and manually try to cause problems, or programmatically try to cause problems with complex scripts and things like that. The Fault Framework introduces a whole new toolbar and associated behaviors that allow you to just mark up any component with a fault type and then trigger that fault to occur. So for example, you might have a proc switch and you have it stuck on or stuck off. Or you might have a signal drift on some kind of an analog device, right? So that was normal operation. Now we're going to start up the fault simulation. And the first thing that we're going to do here is, I think, just test what happens when our machine is cycling and this door opens. Well, it did exactly what it was designed to do. It halted the machinery, closed the door, and they're able to start it back up again. These little capsules in the model, these are drag and drop components that allow you to set up permissive states in the system. So watching for something to be happening, and then do assertions to check that something passed or failed. Now here, we've faulted out a sensor that was watching for the rotation of that turntable. And so the table didn't stop when it was supposed to. Instead, it went all the way to its hard stop. And this caused a problem, and it threw a car body on the ground. And that is a detectable situation. So when we're using the fault framework, that gets logged to the output log. I wish this text would go away. Oh, there we go. Wish granted. Right, so we log, oh, but that stopped the video. There we go. we log all of the things that occur while we're running that test. So it gives us a full report of our entire scenario. Now that fault framework, that whole set of tests that we did, any faults that we've added to the equipment in that model, as we're running that, we're able to record when we trigger them, and that turns that into a reusable test. So it's you can think of it as a regression test that you can run over and over. So maybe we run the test against our logic rev 1, and we find some problems. We then go back and make some changes to our PLC code, and we just run it against that same test again, and can just say, hey, run this series of tests. It'll recall when each fault was supposed to occur, and run another report and see, did we improve our situation or did we make it worse? Another thing that we can do with the fault framework is actually set up, there we go, running that. After running some tests, we can set it up to do operator training. So right now we're running through an experiment manager that's calling up different tests that we've recorded. So each one of these tests, test 1, 2, 3, 4, 5, each one of those is a different series of fault triggerings while the system is running. So we're making certain sensors fail, maybe getting some motors stuck on or off, things like that. And there we go, we got one more to run. So we'll complete running all those tests and we get a report, and we can see what the state of the failures were, which ones were very severe, which ones passed, things like that. And then here's a full log, the whole event log, everything that happened during each of those tests. Now we'll set it up, to run all the different faults randomly. And step through them. So right now we're letting the operator see what's happening, and Emulate 3D tells us where the faults are. So it highlights the equipment and tells us that there's a fault, and we can log a message. Hey, I'm identifying the fault. I'll log that, disable the faults, and continue to run the next test. Then when we're ready to test our operators, we can hit the operator training mode and disable the hints that we give about where the faults are, and the operator needs to find and identify and log the messages for those different faults when they find them, and then continue. So the fault framework gives us visual indication of where things have gone wrong, and we can take that visual indication away so that we can train and test our operators in the scenarios. Go. Now, the next level of operator training, the immersive virtual reality training. And you may have seen this video before on YouTube. This has been out on YouTube for a bit. But again, every model is automatically a virtual reality model, and anything that is a load. So all of the things that we're manufacturing or packing, or the things that move throughout the system, those are what we call loads, and loads can inherently be interacted with. So you can just reach out and pick one up. You can put them down on a conveyor or put them in the trash or whatever you want to do with them, but they're live in the model. You can also reach out and touch HMI screens and click touch buttons and pull levers and turn knobs and things like that. So in this training scenario, we have some additional cues that can't really exist in real life. So you'll see the green arrows that point at the things that, like the next thing that needs to be picked up, and the glowing volumes that you see that tell you how the parts should go and be oriented. So this is teaching him how to do this assembly work. And then, of course, just like in the previous training scenario, at any point we can take away those additional visual cues and let the operator continue on and do more of a test of what the operator has learned. And this is all just live intelligent model. Again, it can be connected to your controls, or it can be running simulation logic and be completely encapsulated. And this works with all of the popular VR headsets out there. So we're agnostic to the equipment. My current favorite is the Quest 3. I like the consumer version better than the Pro version. I think the Pro version is a little bit quirky. but the consumer level one's been really solid. And that's everything I've got to show you in my presentation. And I'm going to move over to some live software next. But before we do, I just want to pause for any questions. Good for now?
Sounds like we're good to go.
What's the difference between
All
this
right.
and factory IO?
I think you're on.
That's me?
Yeah.
Yes, hi. What's the difference between this software and factory IO?
Factory IO is aimed at education. It's got a very fixed library. And Emulate 3D is more designed to allow you, it's more of a, it'll look the same at first, when you look at the polished interface that we have and the drag and drop components from the catalogs. But when we start to go deeper, you'll see that Emulate 3D is really an accelerated development environment that allows you to build any of your custom equipment as well, right? So we use C# scripting with Microsoft.NET, and so you can build Emulate 3D out to do anything, right? It's extremely expansive. Our physics engine is also going to be far more advanced, be able to handle much larger capacity of production of equipment, of live loads. We also have multiple physics modes. So for different purposes, volumetric physics or linear physics, if you need to do very, very large throughput analysis type models. And our connectivity is also not just OPC based. We have dedicated SIP connectivity, and then even SIP1 for Rockwell controls and even for Logix Echo. So that SIP1 is a interface that runs under Windows so that you get the most realistic machine-to-machine type comms. And our emulated device library is also part of that. So we have things like the emulated PowerFlex drives and other like 60-something other modules right now, which is a growing library of things so that when you are connecting up your controls to this in a SIP class 1 protocol, your devices don't have to be inhibited. You actually have emulated devices, so you get completely the highest fidelity possible controls testing experience. Good? Yes, Philip.
Do you have physics that emulates airflow and temperature?
So our physics engine doesn't inherently encompass those kinds of things, airflow and temperature. However, I can tell you that I've recently worked with one of our clients who needed to blow wind on some packages that they were dropping from a drone into a basket, and they were quite satisfied with what we did there. Temperature, we can do some things with in a reduced order type of sense. And in fact, we have temperature components in our process catalog, but it just uses a logical loop and moves quantities, right? So we just, our physics engine doesn't account for thermal expansion and things like that, but you can carry and add and subtract quantities of anything. And so when we talk about managing temperature throughout our fluid handling system, we're just doing that. We're adding, our fluid has a property that holds a value for temperature, and we can add and subtract at that value with any kind of logical loops or operations that we like. So we have the C# scripting to allow you to do complex calculations if you like, to make those things work in a pseudo sense. And we also have a drag and drop logic editor for any component that allows you to do it in a very kind of simplistic but higher level way. So this is live Emulate 3D. I'm running this inside of a VM, And this is live and over the internet, so things might be a little bit jerky in here when I start to animate stuff. But I want to assure you that Emulate 3D doesn't run jerky. It's very, very smooth when you're looking at it firsthand. And you can see my frame rate is always being displayed here, and my model time is always, or my model speed is always here, and the model time is here. I want to just show you a little bit about what our physics engine does. So this is just an absolute base conveyor, and it is to emulate 3D like a line or an arc is in AutoCAD, right? This is an absolute base element in our software. Now, these are properties about that component, and you can see that I can dynamically change the length of the conveyor, or I can go over to the property and input, exact values, and we can use any units that we like, right? So even if my display units aren't currently the units that I want to put in, I can put in things like I can make this 1 meter wide, and it'll take that on, or I can say 500 millimeters, and it'll take that on and convert it over to whatever I'm displaying. So those are some properties of this conveyor. But when I dig in deeper into the properties, so this is the short list of properties, and we can control what's in here from the full list. And now this is the full list, right? So these are parametric. Everything's driven through these properties. And some of the properties that make this component a machine are the motor. So if I look for the motor property and expand that, we can see and set the XL, decel, and speed, turn it on and off, change the direction, and even get encoder feedback from it, right? So that's all part of that machine's motor. And when we start the model, there we go. Now time is ticking. This is really jerky for me, actually, right now, trying to display this through this VM.
It looks fine from here.
Oh, interesting. Okay. For me, my VM seems to be not behave. Oh, there we go. Now it's better. There we go. It is really bad. What's going on there? Okay, I'm going to go native to my desktop. There we go. Recreate that experiment here for just a moment. So turn on the model, and we start generating loads and dropping them onto the conveyor. And again, when they get to the end of the conveyor, because we're in this volumetric physics environment, they fall on the floor. So they're under the effect of gravity, and they're being driven along the conveyor, not by following some kind of a simulated animation path, but by applying force to the bottom of the boxes with the surface of the conveyor. And we can even take a look at that. So we'll go to visualization and turn on the physics view. And then I'll pause this for just a moment. And we can see some information about why the boxes are doing what they're doing. And we can see all the different physics bodies in the model right now. And then in fact, we can turn off the, the actual graphics. And so now we see only the physics bodies at play. So that sphere, that's a congestion zone around the load creator. So we don't want to make another box if there's one already in that space, because you don't want two things trying to occupy the same space at the same time, because that'll make an explosion, and that would happen. Here on this box, we can see these points of contact that we're calculating with the physics engine between the box and the conveyor. And so the blue lines coming down on those points represent the force of gravity pushing the mass of the box down. The yellow lines represent the force vector that the conveyor is applying at that point. And the number is the coefficient of friction between the material of the box and the material of the conveyor surface. And so if we look at what those are, they're just properties, right? So I've selected the box. And if we look at its friction material, it's something called corrugated. And if I look at the conveyor, it's got one called rubber. And those aren't any kind of real world standard. We've not mapped that to anybody's secret list of all materials, but they are names. They're just strings that identify a material. And in the model, there is a table, a matrix that lets us describe the coefficient between any two materials. So if we look at where corrugated crosses rubber, we have that 0.4 that we see here. Now over here, you see those 0.3s. That's where we've got corrugated on corrugated and so on. And we can add materials, take materials away, and change all of the values so that we can tune our physics environment to more closely represent what we see in the real world. So when we're building our equipment and building our test scenarios, we have something that's a little bit more accurate. Now, adding different friction materials to components and doing tests further helps us to do a really great job of testing how our control logic and machinery are going to handle the situations because it's not a perfect simulated environment. We are able to introduce variation in the materials. And so, it's not the perfect environment that we're interested in testing with our controls necessarily. It's the exceptional situations, it's the imperfections that really cause us headaches. And so when we can build that into the model, we can do a better job of controlling the machinery and making sure that we handle everything correctly. Now, everything can have a physics body, and there are different kinds. So I'm going to make a new box here and just resize it. This could be imported CAD, right? It doesn't have to be something I make in here in Emulate 3D. It can be anything, any 3D object. I'm just going to give it another color just to make it shine a little more. Start the model up again, and I'm going to collide my new box with the loads. And you can see that right now, nothing happens, right? They don't even know it's there. This looks like a glitch. Well, this box, if we go and look at its physics category of properties, so these are all the properties just to do with the physics of this object. There's one in particular that's called body type, and that is where we can change it from visual only to being something that will interact with these loads. Now, a sensor is a body type that will detect the presence of loads or deflectors. A deflector is an immovable object. It'll push loads will bounce off of it, but the loads won't have any effect on the deflector. And of course, you know what the loads are. Loads collide with each other, they block sensors, and they can be pushed by deflectors. So if I wanted to make, a little guide bar, deflector is a good physics body for that. And so now, clear out that jam. And you can see again here now how I'm live interacting with the model. I can go in and cause chaos and clear jams and things like that. So I'm backing up the system here. And you can see we're mechanically guiding those boxes to the left. Now, not only can we do that in a static sense, but dynamically as well, right? So think about how we can mechanically build up a system in a very intuitive way, just like we're building machinery out in the shop floor, right? You don't have to think about simulation and animating things. It's equipment, it's stuff. And that is what our physics engine is really designed to do, to take and make a very intuitive way to build material handling equipment, discrete material handling equipment. Now that bar that we've made, I'm manually moving it around by dragging it. But if I wanted to turn that into a piece of controllable equipment, oops, there we go. Let's say we're going to make it a pusher and push things this way. I can use the CAD as the model tools to add the kinematics to that. So we'll first add a joint, kinematic prismatic joint. And that says, hey, you owe me some more information. I don't know what to do yet. So it needs a direction. Which way does it move? Oops. And we just need to find a feature that gives us an arrow pointing the way that we intend it to move. So that's good there. And then we can set up some limits, and I'll set it to inverse kinematic so I can test those limits at first. Let's see, how wide was our conveyor? 0.674. It's a weird size, but okay. So we'll do upper limit. We'll say we'll push it 0.6. That should be enough. Maybe a little bit more. We'll go like 6.5. And then we'll run the model in test mode here. And now I can grab that bar and I can pull it across its axis to and from its constraints there, right? And in this mode too, if you were in virtual reality, you could reach out and grab that and it would act just like this. And if we put the load creator back on, right, same kind of thing, we can push the box. Now, let's go to the next step. We'll turn it back into forward kinematic. And this means that we're going to drive, this is going to be a driven joint. We're going to drive it explicitly. And to do that, we'll add a motor to it. So we'll take a motor and then associate that motor to this joint. And the motor is where we'll describe the performance characteristics. Then on top of that motor, we'll add an actuation controller and associate that. And now, when we run the model, I can just activate or deactivate. And that can be bound to a PLC tag or be connected to simulation logic in the model, right? So you can create whole encapsulated pieces of equipment that just run with simulation logic and or control every low-level operation directly through these kinds of means. Now we might also decide to add a sensor. So we've got a photo eye, put it right there. And a photo eye, everything can be a sensor, but a photo eye looks like a sensor. If we look at that, when the box intersected it, it turned red to let us know visually that there's something blocking it. But it also has this is blocked and is cleared set of contacts. So is blocked right now is true and is cleared is false. Let me slow down the load creator so that we have a chance to do things a little bit easier. We'll make one every 5 seconds. So right now it's blocked. And now it's not blocked, but it is cleared, right? Let me uncheck that. So now that we've got, right, that photo eye and that pusher all set up, that is something that we could connect up to some control logic and look for a signal from that photo eye to activate the pusher. I'm going to try going to my VM one more time because that's where I've got Echo at. And close Emulate 3D here. Start it up here. Let's go to this model. So very similar to what we just built. And now we'll go to Echo, and I'm going to add a controller from an ACD file. Desktop, pusher demo with scale. There we go. Good. So it's creating that controller, and go. It's powered on. We're in remote. And now we'll go to Logix Designer. Open up that same program. There we go. There we go. So very, very simple program. And we can just download that to Echo. There we go. And that's live. Now we'll set it to run. All right, so that's live. So we can see we've got this bit here that we're going to connect up to our photo eye, and we'll activate our pusher when our photo eye detects a box, right? So in the model here, we'll use the I/O browser to connect to find first to connect to that PLC, the Logix, the virtual PLC, and then wire up our PLC tags to the equipment in the model. So we'll add a server here. So we're going to use the Ethernet IP connection. Now this is now searching my network for any controllers that are out there. So it's broadcasting a signal and saying, hey, who's out there? Oh, you are. Cool. Let's connect. So once we connect, we interrogate the program for all of the tags that we can bind to, and here they are. So we'll grab this PE1 and load it. And the pusher, because we used the CITM and we added a controller to it, it put its own placeholder in here for the activate property, that thing that we were toggling, the little checkbox. And so we can just click here and go straight to that pusher output from the PLC. That's bound. For the one that we loaded here, the PE1, we'll go touch the sensor. And then when I click in this property, it takes me right down to the properties I can connect to on that sensor. There's our normally open contact. And that's all we need to start. So I'll start that connection now. It's up and running. The bar turns orange, from blue to orange down here, letting me know that we have a connection made. And then we'll start the physics engine up. All right, so something's happening. We're getting a signal to the PLC whenever we block the photo eye, and it's activating the pusher, but it's definitely not a good outcome. So now we can think about, well, how can we fix this? We could go in and add a delay timer into the software, or we can even just physically move our photo eye in this case. So maybe we drag it down here, make a mechanical adjustment. That looks pretty good. And then one other thing to consider, this little white box. This was just one of those boxes of showing people how to make a scale from scratch. We have scale components in the libraries, but you can make any kind of custom sensor into some kind of custom tool with just a little bit of logic. And in this case, this box it's got a text object to output to so we can visually see it. Its body type has been turned into sensor, and it's just checking each coming load for its mass property. So every object has a mass property. There we go. So every time I pick one, you can see its mass. And we can use that information, and we can bind that to the PLC and make some kind of decision based on what we're seeing the weight of the box is. So let's stop our connection and go back to our PLC. We'll go offline. And we already have a source here to get the weight of the box and turn on a divert bit. So we can just add here this divert bit. So we're going to AND this. So when the photo eye is blocked and this rung is true, we'll activate the pusher. So that rung will become true if the load weight is greater than 1 kilogram. Okay, so let's save that, download it. Okay, and we're up and running. Go back to Emulate 3D, and we'll take that load weight tag, load that up, and connect it to our scale, load weight. Start the connection, start the model. And so now we should only divert boxes that are heavier than 1 kilogram. We can see that's working so far. There we go. So we're able to immediately test the changes that we've made to our program against the digital twin of our equipment model. And that is everything I have to show you today. So open up for any questions before I pass the time over to Kene.
All right. Thanks for setting me up, Michael.
Of course.
All right, let me start my screen share. All right, can you see my screen?
Yes.
sir.
Yes, we can.
All right. So, hey, like I said earlier, I'm here to talk about FactoryTalk Optix Echo, our newest controller emulation platform for the modern controller line. Kind of feel like Michael took a little bit of my flair by demoing Echo in conjunction with Emulate 3D, but that is the whole point of this webinar. So you know all of our emulation, digital twin softwares, and tools that we provide you at Rockwell Automation. So getting straight into it. So I won't talk too much about the advantages of digital twin, as Michael talked greatly to the advantages of it, but just to kind of reemphasize some of the points that he made with Logix Echo, some of the advantages of using an emulated controller versus a physical controller is that it saves time. A lot of us are in the industry where we're not sure which controller we're going to use. If you want to test a new design, we can just use the software to spin up an instance of that controller and test it without ever ordering anything, waiting for shipping costs, or waiting for one of our coworkers to send a controller to get off the controller or send over the controller that we were hoping to use. It helps reduce some of the cost, where if you're not always ordering a new controller, you can just test it through the emulation platform and validate your design before ever buying any piece of hardware. And it just helps increase some of the design flexibility, where, as you saw in Michael's demo, you can connect this to Emulate 3D to fully test out your mechanical and controller designs at the same time. It works well with some API software to even streamline your your design processes even more, and you can use it with a lot more third-party simulation models and some operator training software. All right, so talking a little bit about some of the time savings. We do have a customer who were able to simulate their control programs. So before they were even ordered any of the hardware, anything came in, any of the physical equipment came in, they were able to use tools such as Logix Echo in conjunction with Emulate 3D to test out their whole system and make sure and kind of cut their design time in half. Logix Echo also does give you that optimal design flexibility. With Logix Echo and other simulation software, it is a lot easier to just test out multiple designs where instead of having to build a new part or physically move a part or reconfigure, rewire with the software emulation software, as you saw in Michael's demo, it is just a couple clicks to move things around and test a whole new design without having any physical labor or having to remake parts or rewire them. And just with cost reduction, to the earlier point, as you're saving on those labor costs with these emulation softwares, it does make things quicker, make things cheaper, as you don't have to order multiple PLCs to test with. You can just spin up an instance on this Logix Echo and pretty much work anywhere. As this is a software, if you can have access to you can spin this up on a server, and if you have access to it either through a VPN or remote access solution, you are able to use this from anywhere, any place. So, pretty sure some of you are familiar with our old FactoryTalk with our old Studio 5000 Emulate software. The difference between this and Echo is the new modern controller emulation. So currently it only works with L8s and up, Control, Compact, and the Armor versions of both of them, and the Armor and Guard versions of both of them. But what it gives you is basically this software is just a controller. In the old Studio 5000 Emulate, you'd have to spin up the Emulate version of the controller, then go into your controller and IO tree, delete that, and add the real controller. In Logix Echo, this is really just the controller. So if you're emulating a 5580, you are just using a 5580. You don't have to go into your program and delete anything. You just change the IP address to what your physical controller's IP address is. And doing that, as it is just part of your network, that's what you use to connect it to your different third-party simulation outcomes. So with this being software, you're able to save multiple controller states. So what this means is if you upload one program and you like the way it works, you like the controller, you like the IO tree and the revision that you're using, you just save a snapshot, kind of like with VMs. You save a snapshot of the controller at that time, and you're able to go back to that snapshot at any point of time. This helps with some automated testing. If you're doing factory acceptance testing, you like the way that it's set up originally, you can easily set this up, save this state, reload this state at any time that you like. Like I said, with FactoryTalk Logix Echo, it does only work with L8s and version 33 or later, but it is a fully digital twin of any of the control or command or guard logics or compact guard logics. So it's the same project to a physical or emulated controller, the same IO tree. You can view it in ladder logic, structured text, function block diagram. If you can do it in a physical controller, you can do it in Logix Echo. And as I said earlier, the only change that needs to be made is the IP address. So with FactoryTalk Logix Echo, I kind of alluded to this a little earlier, but you don't need to have Logix Echo on each physical machine. You can spin Logix Echo up on a server and kind of connect to that server to get your controllers. Same way you do for a physical controller. For physical controllers on a network, you don't need to directly plug in your Ethernet. You just need to be on that network to connect to that controller. It's similar with using Logix Echo on a central server. And with this, it gives you the option to remote in and test out these applications with Logix Echo. So As you saw in Michael's demo, configuring the controllers is fast and easy. All you need to do is you can install Logix Echo and make sure you have the right firmware kit. So it's different firmware kit for control Logix and compact Logix and the guard versions of both controllers. But really all you need to do is you go into the software, click add a controller, choose your IP address and revision, and that's it. Then you're able to look for it on FactoryTalk links like any other physical controller. This also gives you the ability to kind of emulate a whole multi-chassis system. So if you have multiple controllers on multiple chassis and communicating either through messaging or produce consume tags, you can emulate this whole system on FactoryTalk Echo. You do this by adding multiple chassis. You can have multiple controllers in multiple different chassis and have them all communicating on the same network, just like you will with a physical system. So with this kind of falls into the emulating with other software. So once you have your control working, your Echo instance set up, you can then use that to emulate your HMI applications, all through a single workstation or by remoting in to contact to the controller on an existing server. With Echo, it also does emulate an SD card. So what this is, it's just a virtual SD card that's stored on a folder. And with this, you can back up and restore projects, read and write data from applications, log it, or anything you would do on a physical SD card, you can do on this virtual SD card. The only difference is that you cannot store any firmware to a virtual SD card. So what this does is, like I said, it works just like a physical controller, where it was Studio 5000, you pull it up on FactoryTalk links, and as it's just like a physical controller emulated, you see that controller in links, and you just connect through the IP address. And as it is just like a physical controller, you can also connect through an IP address of one controller, but if they're on the same emulated chassis, then you are able to go over the backplane to a different controller. So this is just some minimum hardware, that performance hardware that you need to install the software. You do need a good CPU and at least 8 GB of memory. So this is just a screenshot of some of the features that you can do. Like I said, Echo has gotten to the point where it is an exact twin of a physical controller. So you can do SIP motion, you can do safety programs on Echo. So these are the controllers that are available on Echo. Every controller in the L8 family, including control Logix L8s, guard Logix, and compact Logix and compact guard Logix. And you are able to do standard and safety task execution in Echo. If you're using a guard controller, then you're able to do safety tasks. And like I said earlier, you are able to emulate the network of a physical controller, either using dual IP or DLR. No hardware needed for safety, as you can run those safety tasks and safety programs on the emulated controller. Okay, so if you're running Echo on the server and you have only a certain amount of user licenses, the way it works is whenever somebody adds a controller, it borrows a license, and whenever you delete a controller, it returns that license to the server. So that just helps with license management and activation management. And you're able to just directly store log files. So that is all I have in terms of presentations before I get into actually showing the program. Do we have any questions? All right, well, if there's no questions, then I'll get into, oh, I guess, Philip.
And what's a minimum version you can run?
So the minimum version on Echo is version 33. For any earlier versions, you will have to use the original Studio 5000 emulate. All right. If there are no other questions. Okay. So this is the Logix Echo dashboard. As you can see, it's just the devices list where I have one chassis already made, one controller made in this chassis. And this is where you set the IP address and subnet mask. And as this controller is made and it's on the network, I'm remoted into a server right now, but if I look in FactoryTalk links, I can see it on this network, on my emulated Ethernet, and also if I as this exists on the network, I'm able to also access the controller on any device on the network. And then adding the controller to Logix is easy. I'm just going to save this file. Yeah, adding devices, you can either add controller directly, which you would do for any of the compact Logix, or if you're adding a control Logix, you would have to add a chassis first and then add your control Logix controller, just like you would in any real controller. All right. Any questions about actually using Echo or how it would function in comparison to a real controller?
Yeah, Kenny, this is Dwayne. The Logix Echo can exist locally on my own workstation, but I can also use it in conjunction with the FactoryTalk Hub.
Yes, you can. So, Dwayne, thank you for the question. The question was, can you use Logix Echo locally on your workstation, or can you use it remotely through the hub? So the way it would work remotely through the hub is you would have to connect to our remote access solution on the hub to actually remotely access those controllers on a different that's located on a server.
And that would give you the ability to share something across, different platforms, different operators and so on.
Yep, that is correct. So if multiple people remote in, then they will also have access to those same controllers on Logix Echo. And anybody locally on the site will still also have access to those controllers.
All right, thanks.
Philip.
While we're waiting, what the instructions aren't run in Echo? Is there anything in the instruction set that's not possible?
As of version 3, you are able to use any instruction you would be able to use on a physical controller. So you're able to run motion and safety instructions.
Thank you.
Peter.
This is a question more for Emulate 3D. Is that okay?
Yep.
You said you can upload like CAD files. Is that more like STL files, or can you upload like full assembly with mates?
So the way that we do it, right, is we put a plugin into the CAD platform, and you export from the CAD to emulate 3D for most CADs. We can directly import STLs and STEP and IGES and things like that, but the preference is to use our plugins in the tool and export, because we use the CAD's geometry kernel to recreate the geometry in the cleanest form for us, so you get the best quality result, and we do some things to optimize the meshes. We don't use the mates and constraints that are native to the CAD. Apart from that, if you're using Onshape, they use the same kind of joint structure we do, so we automatically interpret those. But we do the inverse of mates and constraints. We use joints, right? And so the reason for that is, if you want to make a very large model with all kinds of moving pieces, with lots of moving pieces, right? It could become computationally very heavy. And when you think about mates and constraints versus joints, when you're using joints, you consider everything is locked down, everything is fully constrained, except for the degrees of freedom that you specify. But mates and constraints is the opposite. Everything is loose and floating, except where you constrain them. And to constrain an object is many more points of data than to consider it completely locked down and give a degree of freedom. And for animation tools that use, kinematic solvers and things like that, joints just work better. The solvers know how to do that work more efficiently. So long story short, but we don't use their constraints. We completely ignore that information, and we use our own. But we put the toolbars into the CAD platform so that you can still do that work in that platform. That information saves with the CAD file, stays with the CAD file. So it's not something that you just do one time and then that work is wasted in trash. It's, if you have common subassemblies that you use, that information will save with those subassemblies, and every time you use them for another greater project, it's just inherently there.
Okay, so you can add joints to assembly kind of easily.
Yeah.
Okay, thank you.
Yep. You're welcome. Thank you.
All right, so I uploaded this big project with all of this I/O that is physically running on a controller right now, just to show that when I go offline and I want to use the Echo controller instead, all I would do is properties. Not even that. All I would do is just change the IP address. You can see I'm going from an actual physical controller to the emulate Ethernet, and you're able to do that. All right, so that is all I had. And Peter, do you still have a question, or is that just the old hand raise?
I think Jermon has a question.
Hi, yeah, I've got a question. Just to confirm, the licenses per controller, is there any limit to I/O or remote racks for Echo?
No, there is not.
Okay, thank you.
I guess when you say to I/O or remote racks, do you mean how many racks are in the Echo software itself, or how many remote racks you can add in the controller tree in the software? I mean, in the actual Studio 5000 program.
Just in Echo, yeah.
There is a limit of 12 chassis running concurrently.
Okay. And then another question, you mentioned taking the data from Echo and I guess working with the third-party vendors or third-party software for checking stresses and other calculations. Could you talk a little bit more about what that looks like?
So the way it would look like is, since Echo is just the emulation of a physical controller, it would be the same as connecting to any one of our physical controllers with the simulation softwares. So for example, with Emulate 3D, Michael, correct me if I'm wrong, that already comes with links installed, correct?
So it doesn't come with links installed. It comes with our own drivers that are that would fulfill the same kind of duty, though.
So as long as the third-party software has our Ethernet IP driver installed, then you'd be able to connect to the controller with links.
Okay, that sounds great. Thank you.
So Echo is available as a subscription only. It is not something you can get as a perpetual fashion. And if you needed 5 versions of Echo running, you would need to subscribe to 5 instances of Echo, correct?
Yes, that is correct.
Okay. And with Emulate 3D, is that also subscription only, or is that something that they could do on a perpetual basis?
No, perpetual is really that's our favorite. We offer all of the software in perpetual and then a subset of it as subscription. There's a little bit of a change that we think is coming in the software structure in the next year or so, but for the most part, it's, there's a few different tiers, right? So it's one software platform, but the different features, the different licenses that you see turn on some different features in the software based on what you plan to do with it. Same model files and everything, right? But you'll see kind of a range of things. So from the bottom, Demo 3D, then Sim 3D, then Emulate 3D, and then Controls Testing, and then Ultimate. The Sim 3D and Emulate 3D controls testing features you can think of as kind of siblings that stack on top of Demo 3D. And Ultimate encapsulates both of those sibling features, right? So it's everything. And the range, well, all the pricing you can see on the portal. Everything's in the e-commerce portal. There's 2 different places you can go into. You can go in and look at perpetual licenses, and there's a separate kind of entry point to get in and look at the subscriptions. When you go in to either of those places and select any of the software products, you'll see some recommended products down at the bottom, and those are to do with different training options. So if you wanted to try Emulate 3D before you buy, there's a program for that called a trial workshop. And the trial workshop gets you a 1-month license and a 5-day, hour-a-day instructor-led online course. And we walk you through, how you touch the software, build a few different projects. So the first 4 days are everybody does the same thing. It's a set kind of projects that we do to learn the fundamentals of the software. And then on the last day, the instructor will take whatever questions people have had during the week and kind of go over any of those questions and do some specific example models. During that whole month, you are treated like a full customer. You have access to our dedicated support team for any questions that you have. You get access to our 1,000+ training videos and guided paths that take that 1,000+ videos and makes a very particular path based on the type of work that you plan to do, right? So that you can see the forest through the trees. And then all of our other self-learning tutorials and documentation and things like that.
Okay.
Once you buy software, there's another training package that is about a 16-hour investment, I'd say, to complete. And that's for up to 6 people for that. When you buy that package, that's only available once you buy a license, or if you buy that with a license. The other one is meant for people who haven't bought a license yet. And I think like that trial workshop one is like $300. But if you are buying software, don't buy that $300 trial, because if you buy software, you can have that for free. The one that you get for 6 people, that is the full 16-hour course, that is like $1,060. And then we have an applications team who will do custom things for you. So there's a training product on there that you'll see called Custom Training Hours. It's a block of 2 hours. You should always talk to us before you buy them to make sure that we're going to be able to use them in a useful way for you, because it is completely custom and because you can do so many custom things with Emulate 3D. But you can buy those hours and use them for things like you can specify a component that you need, a specific component you want to build for your library that you would own. You can hire our team to do that, or to co-engineer a project with you. It's just time with our engineers.
Okay. Does anyone else have any other questions? All right, well, I'd like to thank Kene and Mike for your time today. Really appreciate you going through the presentation. If anyone does have any questions, feel free to reach out to anyone on the automation team. Get in touch with your Turtle salesperson. Again, thank you all for joining us today. Have yourself a good one, and hopefully we'll be talking to you all real soon. Thank you.
Thank you.
Thanks, everyone.
Thanks, everybody.
Thank you.